If you are using a full-size X32 like me, you might have realized the huge amount of different connectors at its back. While working on my own audio over IP protocol, I used my console as a test audio source. On connecting some cables, I realized that I used almost any connector at least once. But there is one single connector I haven't used up to now, and I bet you haven't either. A single USB Type-B connector next to the Ethernet jack. There is no information in the documentation or the internet up to now, and the manual says a short, it's for remote control. If you want to know what this connector does, stay with me. My first idea was to connect an USB cable, look up the vendor and product ID to check what device is connected on the other side. But guess what? Nothing happens. Literally nothing. What is the first thing to do now? Yeah, of course, ask the AI. But even the most recent models are not helpful here. The USB Type-B connector on the rear panel of the X32, not the one on the expansion card slot, is used for remote control of the mixer. What a help. So when AI is not helpful at all, we have to make use of our natural intelligence. Wait, what are these small openings in the housing? The official manual is not telling us anything about them as well. This is a switch. Oh, the console rebooted. Maybe keeping one pressed while resetting? Now we are in business. The device manager finally recognized an USB device, and my console is hanging somewhere in the middle of nowhere. The vendor ID is OX15A2 and the product ID is OX003A. Looking into the USB vendor database, the vendor is Freescale and the product ID seems to be a Freescale IMX25 USB bulk I/O device. During my investigations on the expansion card, I had a deeper look into the X32 core. There, the main CPU is accessible and I had a look on it. It's a Freescale MX253 microcontroller containing an ARM926 core. Wait, this ARM is clocking at 400 MHz and is able to run Linux. Could it be possible to run Linux on the X32? The CPU board has an SD card on it, so my first idea was to use this SD card to upload a Linux image. From the Freescale documentation, I learned in the meantime that the boot ROM of the IMX is trying to load user code at an offset of OX400 of the first partition of the SD card. So let's have a deeper look at the SD card itself. There seem to be 4 partitions, a small 4 MB partition at the offset 2, 2 partitions with 72 MB and 40 MB, and another one with 4 MB at the end. The offset 2 means 2 sectors, each with 512 bytes, resulting in 1024 bytes, which gives us another offset of OX400. So let's have a look at the first partition. In the beginning there seems to be some kind of data, but not so much. So as you can see here, from OX0 to OXCO, OXCF, there is a couple of loose bytes here, but no very important stuff. Okay, at OX400 we have more code. Starting from OX400 we have some bytes that are non-zero up to OX620. So this seems to be a very small bootloader or something like this that the internal boot ROM of the IMX is expecting to load after the booting process. So then have a look in the later areas. Okay, here a lot of zeros. And here's something starting at OX7COO. And again, some data. Let's scroll a bit through this code if we see some useful data. Yeah, there we have some ASCII characters, and let's see what we have here. Oh, okay, 2.05, some hexadecimal values, Wednesday 13th of March 2013. This looks like the bootloader of the X32. New serial engineering. Here are the names of the devices: X32, X32C, the compact, X32P, T8, X32Rec and so on. And here the information DCP. Okay, this seems to be the DCP loader of the X32. To get a better idea what we are seeing here, let's extract this promising data at offset aux400 and put it into Ghidra. This is a decompiler for different processor architectures and it is supporting some of the ARM architectures. It's a bit strange, but according to the documentation, the ARM926 processor contains an ARM version 5T microarchitecture. So select ARM version 5T, and according to a short internet search, Little Endian is the common configuration for this processor type. Hey, we received some code here and the first entry point seems to be valid data. On the left side you can see the binary code we received from the SD card, and Ghidra tries to understand assembly code based on our ARM version 5T Little Endian architecture we selected. And on the right side, it interprets this assembly code and decompiles it in C code. And as you can see here at address 0, we can receive our reset vector. And while looking through this code, it looks very promising. So it seems to be valid code. We can see functions, and with a double click I can open it. And here we see some kind of variables, or at least memory addresses. And aux8 is directing to our RAM. So this seems to be variables within our RAM. And let's have a look here. We can see some do while loops. We can see a lot of different calculations here, and we see some sub-functions here. So let's open this one. Okay, yeah, seems to be valid code. And here we can see this variable, for instance, is directed to aux53 FDC000. And if we look this in the reference manual, 53FD, 53FD0, FDC, this is related to the watchdog. So this might reset the watchdog or disable it. So yeah, it's looking promising here. It took me a couple of hours, but I figured out that the whole first partition of the SD card seems to be copied to a higher RAM address. This leads to an offset of our mini bootloader at address aux83C 00800. I found a lot of fixed registers of the IMX25 processor and was able to give a lot of the decompiled generic function names a human readable name. So here you can see the reset of the watchdog, the initialization of the UART, and code for initializing the connected LCD together with the correct GPIO settings in the IOMAX-C register. Even the initialization of the SD card and the USB host can be seen within this code now. So I got a pretty good idea of what's going on during the boot process, including the load process of the firmware itself. So this could be an option to start a Linux system on the IMX25. But the SD card within the full-size console is below 2 PCBs, and I do not want to disassemble the whole thing. But there's another option. Freescale offers a serial download protocol over an USB connection, and the USB Type-B connector is connected to our processor. This seems to be a more convenient way. As the IMX25 is on the market since more than 15 years, there are different tools to upload code over USB. The official Freescale ATK, manufacturing tools, 3U, IMX USB loader and PyATK. Unfortunately, the IMX25 is not supported by the most recent tools like 3U and IMX USB loader, and the older tools like Freescale ATK has dependencies I could not manage to fulfill with the modern Debian system. But PyATK looks promising as it uses Python and supports at least Python 3.4. So I cloned the repository, installed the dependencies in a virtual Python environment and tried to start the tool. As I'm using Debian 12 with Python 3.11, there was a minor problem with the code, but I could fix this by changing 3 lines of code. A first test looked promising and the IMX25 was detected successfully. Regarding to the reference manual of the IMX, the start procedure looks like this. After power on reset, it loads the ROM, which starts USB and enumerates it as a dedicated device like an HID device. The host computer then has to initialize the memory and sends a program directly to the RAM. After the upload has finished, the serial download program will jump directly to this first byte of the uploaded code. This means we have to write a very small test program to see if the memory is initialized correctly and the upload is working well. Furthermore, we seem to have full access to all registers using this protocol, which is pretty nice. Looking at my X32 core CPU mainboard, the X32 uses 64 MB of LPDDR RAM from Micron. It took me a while to read the 2596 pages of the IMX reference manual, but I found the important registers to initialize the LPDDR RAM together with the decompiled C code. With this information, I created a memory initialization file for Pi80K. The only thing we need is a small test program that turns on an LED or something comparable. The IMX253 has a single PWM output, so let's give it a try and write a small program that turns on this specific output and see what happens. Hopefully no internal voltage regulator that blows up something when we set the pin too high. As we do not have any kind of operating system yet, we have to program the controller bare metal. This means assembler or C. I found a small assembler skeleton for the IMX25 in the internet, so let's try to initialize the PWM output and set it to a logical one. From the reference manual, I learned that we have to switch the IO max C register to the desired function, set the pin direction to output and set the output to the desired value as in other comparable microcontrollers. The PWM output can be routed to a standard GPIO function. Okay, the boot ROM should jump to the first byte of the uploaded code once the upload has finished, so we have to make sure that our reset handler is placed at the very first byte of our code using a map file. Now we can compile and link this small program and upload it to the X32. Let's see if something happens. If I'm lucky, the fan or the display backlight will turn on when it is routed to the single PWM output of the processor. Let's see. And upload. Ha! Do you see this? The lamp is on. Okay. But still there's nobody at home, but we can run our own code on the X32 without opening the device. That's pretty cool. Now that we are able to run our own code, we can think about more. Several years ago, Freescale offered a so-called LTIB, a Linux target image builder. It would be great to start Linux on the X32, right? But since Freescale has been acquired by NXP in 2015, it is quite hard to get the necessary tools for the IMX25. At least a consistent documentation is missing. But the mainline Linux kernel itself has support for the IMX25. To start the Linux kernel itself, a tool called U-boot is very common, so let's try to get this thing up on our IMX25. It took me a while to find the right U-boot version that supports the IMX25 and is able to work with recent versions of the compiler toolchain. U-boot in version 2020.10 seems to be the last version that supports our processor, so let's check out this version. The common way to configure the U-boot is using the menu config. First we have to create a default config for the IMX25. U-boot supports the MX25 PDK, a product development kit from Freescale, so we use this as a basis for our journey. Unfortunately, the U-boot does not support the Linux device tree for our board, so we have to initialize the board using plain C files. Again, we should try to initialize the lamp to see if the C code is called correctly. For this, we have to edit the file MX25 PDK. U-boot has some convenient macros to deal with the hardware. Within the board init function, we can put the IOMAX and GPIO configurations with convenient C code. If our code works correctly, the lamp should turn on, like in our small assembler program. Let's try to compile the U-boot using a compiler for the ARM architecture, ARM NaN ERB GCC, as we are compiling it for a bare metal system. As my system is an x86 based system, I have to call make using arch equals arm and cross-compile to call the desired compiler. And after some time we receive an uboot.bin. Let's try to upload this to the RAM. As the lamp didn't turn on, I tried a different setting of the GPIO configuration. I had no clue why the GPIO wouldn't go too high, so I thought I set the GPIO as an input by accident, but no. So I searched the linker script of U-boot to see if the start address is placed at the expected address at the beginning of the RAM, but this was the case. So I went back to the menu config and tried to find the problem there. I placed the U-boot at a slightly higher address to make a space for the small assembler program I used in the beginning. This program will then jump to the start address of U-boot, but without the reset function of U-boot. Okay, finally it worked. There were several problems here. U-boot seems to reinitialize the memory if you do not stop it. And there was an initialization file for DDR2 RAM, and the Behringer board uses LP DDR RAM, so there was a problem. And obviously U-boot needs to know where it is in the RAM, otherwise it tries to rearrange and copy itself through the RAM, and yeah, this was another problem. Now I placed it at the start of the RAM, and yeah, now it is working. C code is running, good sign. Oh man, to see if U-boot is working well, and of course later on the Linux kernel, it would be great to use a serial terminal. Looking at the PCB of my X32 core, I realized that the MIDI ports are connected to our controller. As MIDI is a serial connection, a small adapter with some passive components should work to connect my computer to the IMX25. First I had to reverse engineer the MIDI circuit to understand what converter I will need. To cut a long story short, it took me a couple of hours to understand two things. The IMX UART needs a clock from the clock distribution system of the IMX25, and the MIDI connectors are routed to UART 5. But in the end, the boot process looks now like this. Now that we have a working U-boot, we can venture into Linux itself. Back in the days when the IMX25 was the hot stuff, Freescale suggested the kernel in version 3.0. As this kernel does not support the so-called device tree, it was not within my scope. Device tree is a data structure and hardware description language for Linux to support different types of controllers, peripheral components like real-time clocks, and PWM modules or displays. After a lot of investigation and testing, I figured out that even the most recent version of the mainline kernel has support for the IMX25, but it is a bit hidden. First, let's clone the mainline Linux kernel from Linus Torvalds directly to our machine. Similar to U-boot, we can configure the kernel using the command make menuconfig. Unfortunately, the kernel does not have a default configuration for the MX25, so we have to start from scratch. The first time I did this, I did not find the configuration options for the ARM architecture either, but I missed to start the menu configuration with the arch equals ARM option. But still, there is no entry for the IMX25 at the first glance. More by accident, I tried the default configuration for the 20-year-old MXS processor, and guess what? Now the IMX25 can be selected by the menu. There must have been some dependency problems before. Anyway, we can configure our system now. First, I like to test a very basic kernel configuration. If this is working well, we can test a more comprehensive one later on. Most important part is the UART to see if the kernel is booting up correctly. Well, the kernel should be configured with the bare minimum information now because we are using the MXS default config. But I have to tell the device tree that it has a 5th UART, so I have to edit the device tree files to enable the UART number 5. And here's the special thing. The UART 5 is not at the UART 5 TXD and RXD pad, but on a different pad, so I have to look into the reference manual. It's TXD is at ECB and RXD is on LBA pin. So let's search for another UART1 and just copy it to UART5. And we have no RTS and CTS. And here I have to configure UART5 pin control. So I think that's it. Let's have a second look. UART5 group. Yeah, this should be fine. Okay, that's it. And now we can compile our Linux kernel with the cross compiler. So arch ARM and cross compile with user bin ARM none EAB make z image, because I like a compressed image here. It seems to be very common to start the kernel using a wrapper format for the U-boot. So let's convert the Z image into a U image using the command make image. I'm aware that the U-boot maintainer calls this strategy pretty stupid, as each kernel image has to bring its own decompression algorithm, but if it is working, I'm fine with it. So let's reconfigure U-boot, recompile it, and put all binaries together, upload them to the RAM and see if something happens. As we want to start the kernel with the UART5 in mind, so I have to redirect the console to UART5. And the baud rate is 115,200 baud. And the console 2 should be routed to TTY0. So now we have to tell U-boot where to find the kernel, and we are using the command bootm, followed by the address of the kernel. We are using no init-ramfs at the moment, so we are placing a dash here. And we have to place the device tree blob somewhere. And I'm choosing the address aux8080, followed by 4 zeros, 2, 4, 6, 8. This is looking good. Now we can place some echo here to tell that we are starting the kernel. Okay, maybe one last thing here. U-boot expects an information where it is placed in the RAM, and in my first tries I placed U-boot at the very beginning of the RAM, here at this address, but I faced some problems with different versions of U-boot, and some of them won't start without some problems. So I've written a very short assembly program to be started at the very beginning of the RAM that jumps to a specific address in the RAM, starting U-boot or doing other stuff. And this program is very small and take only a couple of bytes, so I place U-boot at offset aux80 and then some zeros, C0. And yeah, this is our base address for U-boot. The kernel is then still at the address aux80.060.000, and yeah, let's merge everything together and see if something happens. But first we have to recompile U-boot. So use arch arm, cross compile with user bin arm none EAB and make. Okay, let's copy our binary file to the compiled folder. Okay, and now the only thing that is missing is the device tree blob that was compiled during Linux was compiled. So let's copy this. It's an arch arm boot dts nxp and then imx25 pdk dtb, and let's copy this to compiled folder. So now we have everything together. We have a U image for the kernel, we have U-boot, We have the mini loader that is placed at the very beginning of the RAM and the device tree blob. And now we have to merge those 4 files together. So let's use dd, and the input file is our mini loader. Output file is temp, and now, yeah, Linux image.bin. Block size is 1, and we do not want to trunk the file. So that should be fine. Great. Now we have to place our U-boot. The same output file, but now we want to jump at a specific address. So let's use seek at oxco, and I think that should be it. Okay, and now copy the Linux image. This is the U image, and here we need a different offset. Here we need the offset 60,000 that is placed as the offset in U-boot. Okay, 4.3 megabytes. And now we have to place the device tree blob with the hardware configuration. So X32 PDK device tree blob, and we need a different offset. The offset the same as placed in our U-boot configuration. Yep. And now we have an image with 8.1 megabyte, and we can upload it to the console and see what happens. So I have to open a terminal program. It's connected to TTY USB 0. That's fine. Okay, and then we can upload the binary blob using our Python script. So we placed it here at the virtual environment, bin pyth3 mx toolkit run for the board MX25, and we have our Linux image in the temp folder, and we want to place it at ox80000000 with the memory initialization file, and let's see what happens. It uploads. Okay, the lamp goes on, and U-boot is doing something. Booting kernel from legacy image at offset ox8006 and then 4 zeros, that's fine. He recognizes the name, the image name Linux-kernel, that's fine. He recognizes the device tree blob, that's fine too. Yeah, but then nothing. Starting kernel and nothing happens. After some research, it turns out that I used the wrong compiler. For a bare metal application like U-boot, we have to use ARM non-EAB. But for starting the Linux kernel out of U-boot, we have to use ARM Linux GNU EAB. So let's try again. Okay, I think that's the best kernel panic I've ever seen. Okay, what is here? SPI driver. Cannot open root device dev ram 0. Okay, I did not give him some init ramfs. And the kernel panic is only because the kernel is unable to mount the RootFS. Yes. My goal is now to boot into a shell and initialize the most important components like the display, Ethernet and maybe the USB controller to connect a keyboard or a USB thumb drive. So let's create an initial RAM disk to store some applications. And we can clone Busybox with the most common Linux tools for this task. So let's try it. While Busybox is compiling, I activated some more features in the Linux kernel. From some replacement display advertisements for the Behringer X32 display on eBay, I know that it is a 7-inch display made by Innolux. I searched for some promising displays and found the Innolux AT070 together with some examples from Freescale using this type of display. From the datasheet of the IMX25, I've got the supposedly correct multiplexer and pad configurations for the display and the USB host, which we have to place inside the device tree file as well. But first, let's create a new RAM file system using the cpio command piped to gzip to create a compressed file system. Okay, we have our init-ramfs now, our root file system, but we need an initialization file for Linux, so I have to edit the init script. So we have to compile our Busybox into a single file, and I use the find command, print 0 and pipe this into cpio. Null ov, format is new C, and everything should be into init-ramfs.cpio. Yeah, and then we can gzip everything, and we are getting an init-ramfs cpio gz. Okay, and then we can use make image again. A ARM, O Linux, T RAM disk, C gzip, address is 0, entry point is 0, and the name is RAM disk image, and we are using our init-ramfs cpio gz, and we want it here to uramdisk.bin. Yeah, and now we have to tell uboot where to find this uram disk. So I go to uboot and edit the config file for our MX25 PDK. And here at the end we have the dash for the RAM disk address, and we have to change it to aux8081 and then 4 zeros. Yeah, and I have to tell the kernel over the boot arguments what to do with the mounted image. So I want to initialize my init script, and the init rd should be aux8081 and 4 zeros. So he should try to load this init RAM disk at this address, and uboot knows where to find the uram disk image. Okay, let's recompile uboot. Arch is ARM, cross compile, user, bin, ARM none EAB, make. So let's copy our new uboot image to the compiled folder. Now our memory map looks like this. 384 kilobyte are reserved for uboot, 80 megabyte reserved for the Linux kernel, and 64 kilobyte for the device tree blob. The RAM file system is then appended at the end. Okay, now let's edit the merge script and add the uram disk at the end of our binary blob. And as you can see here, I've added another line at the end. I added in total of 100 bytes of the def0 device, so simple zeros at the end of my binary file, because it turned out that the serial download protocol, or at least the Pi80K implementation, has some problems. Sometimes it cuts several bytes at the end of the binary blob, and this was one of the problems why I couldn't start the kernel before. So place our uramdisk.bin in the output file, temp linux image.bin, block size is 1, no truncation, and we want to place it right after the device tree blob. The device tree blob is only 64 kilobytes in size, so we can put the URAM disk at the end. Okay, so merge everything together. Yeah, okay, so start Minicom and upload the system again. Okay, the lamp is on, U-boot is starting. He found the RAM disk, he detected it as gzip compressed, that's fine, and the kernel is starting. There's the login screen, so great. Let's see, root, password none. Okay, I don't know the password for the shell login. But that's another problem, we made it. Yes, init-ramfs. It started and he detected the USB controller. Hey, cool. Ha! There's no username. Yes, we see the files and the folder structure and Linux is running. So let's see what devices we have here in the dev folder. Bus, USB, 001. Okay, let's see if LSUSB is working. This is looking promising. He found an EHCI host controller, so let's see if the thumb drive is working. Not yet. Different type. Yes! It took me a while to figure out the details of the hardware, but after a couple of days I managed to enable the display and the network PHY on it. So up to now we have a full-featured Linux on the X32, so let's call it Open X32. And we can start very nice software on it now. Next to emulated software like Mario, we can run software frameworks like LVGL without problems now, as we have direct access to the frame buffer of the display. A former colleague once said that a complete life includes having compiled the Linux kernel yourself at least once. This project was not really planned, and I stumbled across it during working on the already mentioned audio over IP protocol. But I was able to learn an incredible amount of ARM technology, the Linux kernel and cross-compiling in a very short time. If you have some ideas what we can do with this open source operating system for the X32, please let me know in the comments or feel free to support the work on this project. All codes and changes of the Linux kernel are published on my GitHub repository. A future goal could be the upload of the FPGA bitstream of the original firmware to initialize the audio system of the X32 and get information from the fader boards, but that's for a future episode. If you like the projects I'm doing, then please consider a subscription to this channel and have a look at my blog under chrisdevblog.com, where you might find some more ideas for your own projects. That's it for now, thanks for watching and see you next time.